Okay, so let's start. So recall that we started out with deriving tail bounds for random variables. Essentially, we want bounds of the form probability that x is greater than or equal to mu times 1 plus delta, right? And in the beginning, I proved Markov's inequality, which was valid for non-negative random variables. And we had a bound which was the form probability x greater than or equal to t is less than or equal to expectation of x divided by t. And we used that, we strengthened that to get the Chebyshev's inequality, which now gave us a 1 over t square kind of a dependence, right? So the probability that the absolute value of x minus mu is greater than or equal to t is less than or equal to the variance of x divided by t square. And in the previous class, we got an even better bound, in fact, an exponential tail bound. So we showed that probability of x is greater than or equal to t is in fact decaying as something divided by e to the lambda t, right? And this was sort of a general bound, a family of bounds called the Chernoff bounds. And in class, we proved that the probability that x is greater than or equal to t is less than or equal to the moment generating function of x divided by e to the lambda t. And this holds for all lambda greater than 0, right? You can prove a similar tail bound for the lower tail. So this is 1/2. So this is the right tail of x. Similarly, you can prove a bound on the left tail of x. So once again, you can prove that probability that x is less than or equal to t, where t is now less than 0, is less than or equal to e to the, again, the moment generating function divided by e to the lambda t, but now for all lambda less than 0, right? So it's very symmetric in that particular sense. Okay, so we derived a proof for this particular inequality, and again it was essentially based on the Markov's inequality, right? We're applying Markov's inequality but on different random variables. So instead of applying Markov's inequality directly on the random variable x, for Chebyshev's inequality we applied it on x minus mu the whole square, but now we are applying it on e to the lambda times x. Right. And so we derived a proof of this, but then we noted that this bound depends on lambda, right? So this inequality is true for all lambda greater than 0. So in fact, it makes sense to get the best possible upper bound, right? So this is also true for the minimum. Even if I take the minimum of the right hand side over all possible lambda greater than 0, it's still a valid upper bound, right? And so we are trying to get the best possible upper bound. In order to do that, I have to take the minimization of the right hand side, or in other words, that essentially corresponds to taking the maximum of the exponent, which is just lambda t minus psi x of lambda, where psi x of lambda is basically the log moment generating function. So you can view this quantity, psi x star of t, which is the best possible Chernoff exponent that we can obtain. This can be viewed as a transformation of the log moment generating function, right? So we have the log moment generating function, which is a function of lambda. And now I'm taking the maximum of this particular quantity over all possible lambda greater than or equal to 0. And that gives me a new function, now a function of t, right? So you can think of this as a transformation from psi x to psi x star, and this is called the Kramer transform of psi x, right? So to get the best possible Chernoff exponent, or the best possible Chernoff bound, you first compute the log moment generating function of the random variable that you have, and then compute the Kramer transform of the log moment generating function, and that gives you the best possible Chernoff exponent. So you can try to do this for whatever random variable you have. And this turns out to be easy in some cases. For certain special cases like the Gaussian or the Bernoulli or gamma random variables, you can compute the best possible Chernoff exponent. But in many cases, the PDF itself might be very complicated, or computing the moment, you may not be able to get a nice closed form expression for the log moment generating function. So in those cases, we have to rely on slightly weaker bounds, so basically relaxations of the Chernoff. And that will be our way forward eventually, right? So the gold standard is the Chernoff bound, but the Chernoff bound may not be computable. You may not be able to get a closed form expression for the Chernoff bound in many cases. So we'll try to relax that. We'll try to generalize. If we have a general class of random variables, can we obtain similar bounds? So that's our goal. All right. So in the previous class, we took one particular example, and that was the Gaussian. Right? We evaluated the Chernoff exponent for the Gaussian, and we obtained a tail bound. And we also observed that if you have a general sequence of IID random variables, then the Chernoff exponent for the empirical mean of those random variables turned out to be simply e to the minus, so it turned out to be n times the Chernoff exponent of one of those random variables, right? So in fact, if the tail bound for a random variable x decays as e to the minus psi x star of t, for the empirical mean, it in fact decays as e to the minus n times psi x star of t, right? So we showed that for any general random variable for which psi x star of t is something that is positive, the probability that the empirical average deviates from the mean by an amount t, in fact decays exponentially in n. So any questions so far?
We have to tighten on the right side.
Correct. We want the tightest bound on the right hand side. Correct. Correct. We can take any lambda we want. So if we have some nice expression that we can compute, and if we are able to maximize this particular quantity, then fine, everything is good, right? And again, this works for some kinds of random variables.
So we come to this point for everything. Here we have to see whether it is possible or not.
Maybe. For now, this is what we will be doing, but very quickly we'll get into more complicated random variables where this approach will not work, right? But still, we'll somehow be trying to use the Chernoff bound or some relaxation of the Chernoff. Maybe we can do an approximate maximization, all right? Or maybe the random variable in question is something very complicated. For example, what if it is, right now we're just looking at random variables for which we know the PDF, or sums of random variables, essentially, right? What if I have a more complicated function of the random variable? Can I still get a similar exponential tail bound? For certain kinds of functions, it turns out that yes, we can get general tail bounds, right? But we'll see that a little bit later.
For certain class of functions, we get
correct. For certain classes of functions, for certain classes of random variables, we have these general tail bounds. Right? And we'll see applications of each of these along with it. All right. So in today's class, we'll see a couple of other examples. Right? So in the previous class, we looked at the Gaussian random variable. We saw that the moment generating function is equal to e to the lambda square sigma square by 2. And we computed the Chernoff exponent and showed that if you have a sequence of n IID random variables, all Gaussian with zero mean and variance sigma square, then the empirical average, the probability that the empirical average deviates by an amount t is less than or equal to e to the minus n times t square by 2 sigma square. You can prove a similar bound for the other tail, probability that 1 over n summation I equal to 1 to n is less than xi is less than minus t for some t greater than 0 will also be less than or equal to e to the minus n times T square by 2 sigma square. This is not hard to prove. It's again essentially using the same approach that we followed so far, but instead of the right tail, we're just looking at the left tail. So in other words, the probability 1 over n summation I equal to 1 to n xi. So the probability at the absolute value deviates by an amount greater than t. What can we say about this? And why is it twice? Yeah. Why can I add the two? Correct. So this event is basically the union of this particular event and this particular event, right? So if I call this event A and this event B, then this is basically equal to the probability of event A union event B. Do we all agree on this? Okay. So what do you know about the probability of the union of two events? Do you have an upper bound for this? So it is less than or equal to, so it's less than or equal to probability of A plus probability of B. So it is in fact equal to probability of A plus probability of B minus probability of A intersection B. But probability of A intersection B is something non-negative. Therefore, this is less than or equal to probability of A plus probability of B. This is just the union bound. Is it a disjoint union? In fact, it is not. It need not be a disjoint union. Okay, so the probability of A plus probability of B so I have this union bound, right? So what can I say about this? This is less than or equal to, again applying Chernoff's inequality, this is less than or equal to 2 times e to the minus n t square by 2 sigma square. Correct? Just by the Chernoff. So in general, as long as I have a symmetric distribution, if I have a bound on the right tail, I can also get a similar bound on the left tail. That's easy to obtain. Okay. Now let's see another example. Let's take the example of Bernoulli random variables, simplest random variable we have in question. Let's assume that x is Bernoulli P, and let me define, or let me take y to be Bernoulli P and x to be y minus expectation of y, just so that it's a symmetric random variable, right? Basically zero mean. So what is expectation of y? 1 with probability p and 0 with probability 1 minus p. So what can I say about x, the distribution of x? What is expectation of y? Expectation of y is p equal to p. So x is 1 minus p with probability p and it's equal to minus p with probability 1 minus p. Correct? Okay. What is the moment generating function equal to? Expectation of e to the lambda x for some lambda greater than 0. How many values does x take? 2 different values. So this would be, so what would this be equal to? The first value is e to the 1 minus lambda times 1 minus p. Times the probability that this occurs, which is 1 minus p, plus probability p e to the lambda times minus p. This happens with probability 1 minus p. So just take e to the negative lambda p outside, e to the minus lambda p times e to the lambda p e to the lambda plus 1 minus p. Okay, so this is the moment generating function. The log moment generating function would be log of expectation of e to the lambda x, which is just minus lambda p plus log of p e to the lambda plus 1 minus p. Correct? Okay, let me try to compute the Chernoff exponent. So psi x star of t is equal to supremum over all lambda greater than or equal to 0 of lambda t plus lambda p minus log p e to the lambda plus 1 minus p. You all agree? So once again, I can take the partial derivative with respect to lambda and set it equal to 0. What do I get? It is t plus p minus
1 by p lambda 1.
p e to the lambda divided by p e to the lambda plus 1 minus p. Right? So this is equal to 0. So what is lambda equal to? E to the lambda and lambda. So t plus p equals p e to the lambda by 1 minus p plus p e to the lambda yeah
P plus p times 1 minus
t plus p times 1 minus p
1 minus
1 minus p plus p
times
times p. So
Four.
it is 4 times p. Okay. So lambda is basically log of this. Okay, this looks a bit complicated, but let's plug it in into this, right? So I have lambda times t plus p. Let me call this lambda star. T plus p minus log p e to the lambda plus 1 minus p. Right? So this is t plus p times log of t plus p into 1 minus p divided by 1 minus t plus p into p. Minus log of p e to the lambda star is log of 1 minus p plus p e to the lambda star. So p e to the lambda star would be t plus p into 1 minus p divided by 1 minus t plus p. So let's try to simplify this. This is equal to, I'll split this into a couple of terms, t plus p log t plus p by p plus the remaining terms. T plus p log of the remaining term would be 1 minus p by 1 minus t plus p. I'll also try to simplify this. Log of 1 minus p into 1 plus t plus p divided by 1 minus t plus p. Right? You're with me so far? Plus t plus p log 1 minus p by 1 minus t plus p minus log, what does this simplify to? 1 by 1 minus t plus p. So this is 1 minus p divided by 1 minus t plus p. Correct? So this is also equal to t plus p log t plus p by p plus, so let me take the negative of this. So this is log minus log 1 minus p by 1 minus t plus p, or plus log 1 minus t plus p by 1 minus p. Right? And I see that within the log, both these terms have the same quantity. So this is 1 minus t plus p times log of 1 minus t plus p by 1 minus p. Okay, this is fine. Yeah.
So in this case, we're just shifting the random variable that is p, right?
Correct.
So t will just become t plus p. The arguments of it.
T would become,
T would turn to t plus p because you're adding your summation 1 by n.
yes,
Right?
true.
So that the way you're calculating it, that
Correct.
is from zero.
Correct.
You're shifting.
Correct.
You're calculating the factor
True.
which it shifts from the
Yes.
shifted one.
Yes. Yes.
So directly you could tell that t would transform to t plus p.
I could do that. Yes, that's true. But I wanted to sort of do it from the very beginnings, because this is what I'm really interested in, is the random variable x minus expectation of x. I want a zero mean random variable because it will just make things conceptually simpler. But in principle, yeah, I could just calculate the general Chernoff bound and substitute t equal to, instead of t, I just substitute t plus expectation of x. Right? Okay. So for those who've taken the information theory course, does this expression look familiar? What is it? Correct. So this is equal to the KL divergence between two distributions, Px and Qx, which is, what is Px? Let's say 1 and 0, or I should say, correct. So I think I should instead represent it as a tuple. So Px is, let's say t plus p, and 1 minus t plus p, takes two values, doesn't matter what those values are, but it takes one of those values with probability t plus p and the other value with probability 1 minus t plus p. So it's a Bernoulli t plus p random variable. And what is qx? It's Bernoulli p, right? P and 1 minus p. So I'll represent this as, just for convenience, t plus p. Okay, so this is one of the best possible Chernoff bounds that you can obtain, right? And in fact, in your homework assignment, you have a similar question to derive this, but using a different approach, essentially using Stirling's approximation. So for the case of the Bernoulli random variable, you can use other tricks, right? But on the other hand, if I have a slightly more complicated random variable, then I can't use approximations of the distribution itself. I will need something stronger like Chernoff. Okay, so what does this tell me about the mean of, the empirical mean of IID Bernoulli P random variables? Or IID distributed according to X, which is 1 minus P with probability P and minus P with probability 1 minus P. What can I say about this? So what was the relationship that we derived between psi star for the mean and psi x star? Yeah. So this is just less than or equal to e to the negative n times psi x star, which in this case is the KL divergence between T plus P and P. Correct? So let's try to get, again, because we don't have a better feel for the KL divergence, I'll try to use a bound for the KL divergence, because I can understand polynomials better than quantities like the KL divergence. Right? So it turns out that the KL divergence between T plus P and P, this quantity is greater than or equal to, so I'll write it in a slightly different way. So P into 1 plus delta and P is greater than or equal to delta square p by 4. So let's just use this as a fact. You can prove this separately, but for now, let's just use this as a fact. Another fact, which again you can derive using a similar approach, is that for any t positive, summation I equal to 1 to n xi is less than or equal to minus t. So for the left tail, I can get that this is less than or equal to e to the minus n times the KL divergence between p minus t and p. Again, this is valid only if t is less than p. So if I sort of combine these two together, I get that the probability 1 over n summation I equal to 1 to n xi is greater than or equal to, let's say, p delta. This is less than or equal to 2e to the negative n times delta square p divided by 4. So again, this is not the best possible bound, because the best possible bound would be in terms of the KL divergence, but this is good enough for us to work with for now. So now that we have this, we can use it in a number of other applications, right? And let's see some of those applications. So the first application we look at is one of random graphs. Okay, so let's consider a random graph where between every pair of vertices, you put an edge with some probability p, and with probability 1 minus p, there is no edge between the two. Okay, so this is what is commonly called an Erdos-Renyi graph. So it is a graph with vertex set equal to, let's say, 1, 2, 3 up to n. There are n vertices, and you take any pair of vertices. This is an edge with probability p somewhere, some parameter, and this is not an edge with probability 1 minus p. So whether there is an edge or not between a pair of vertices I and j is basically a Bernoulli p random variable. But in this case, we won't take p to be fixed, not necessarily fixed. I'll allow p to be a function of n, okay, because this gives us the graph in different regimes. So if let's take a general p, which may or may not depend on n. What is the average degree of a particular vertex? So let me say that di is the degree of vertex I. Okay. Now, what is di equal to? It is the total number of edges which are incident on I. I can write this as a summation from j equal to 1 to n, but j not equal to I. I'll count the number of edges. So between I and j, I'll count a 1 if ij is an edge, and I'll count a 0 if there is no edge between I and j. Correct? What can I say about the expected degree? So it's expectation of this sum, which is basically like, since by linearity of expectation, j equal to 1 to n, j not equal to I, of expectation of the indicator random variable. But what is the expectation of this indicator random variable equal to? It's equal to p, right? Because it is 1 with probability that ij is an edge, which is p. So it is 1 with probability p. This random variable takes the value 1 with probability p, and it is 0 with probability 1 minus p. Correct? So this quantity is simply p. So what is the expected value of di? It is n minus 1 times p. So this is all well and good. So this is the degree for one particular vertex I, and it holds for all vertices I. So let me ask the following question. What is the probability that the degree of all the vertices is very close to n minus 1 times p? Right? So what is the probability that di lies in the range n into n minus 1 times p into 1 plus or minus delta? It's within a delta fraction of this expectation. So this for all I. Now, if I think of the degree of I as a random variable, what can I say about di and dj? Are they independent? If I take two vertices I and j, so di is a random variable, right, with expected value n minus 1 times p. dj is also a random variable with expectation n minus 1 times p. Are these two random variables independent? How many say yes? They are independent. How many say they are not independent? What about the rest? So they're in fact not independent, right? Because there's an edge, there could be an edge between I and j. They're kind of very weakly dependent because it's only that edge between I and j which kind of matters. But there are also common neighbors, right? There are a lot of common neighbors. So, but the other neighbors are connected to vertices I and j independently. So in general, they're going to be dependent. So I can't simply say that this is the probability. I can't say write this as a product of probabilities. I can't make that independence assumption here. Okay. So I want to understand this particular probability. So let me try to understand the complement of this, because that will make it easy. Okay. So I want the probability that di is in this particular range for all I. So what is the bad event for this particular case? So let us look at the probability that di is not in this particular range. So it's either greater than or equal to n minus 1 p into 1 plus delta, or di is less than or equal to n minus 1 times p into 1 minus delta for at least one I. Correct? So this is the bad event. All right. Now again, the di's are not independent random variables. So what can I do? Can I get a bound on this in terms of a probability for specific di? So let me call this particular event that di is greater than or equal to this, or di is less than or equal to this, as an event ei. Okay. What is this probability in terms of the events ei? Or in other words, in terms of set operations. Yeah. It's the union, right? So if any one of the EIs occur, it's a bad event for me, correct? So that's simply the union of the EIs. Now what can I do with this? So I can simply use the union bound, which is less than or equal to summation I equal to 1 to n probability of EI. Great. Now what about each EI? So firstly, are the EIs independent? No, they're not. But are they identically distributed? So it's symmetric, right? So they're identically distributed. So this is equal to n times the probability of any one EI, let's say E1. But what about E1?
We have union there.
Okay, so I have a union there, but what kind of an event is this? So E1 is the event that di is greater than or equal to n minus 1 times p into 1 plus delta, or di is less than or equal to n minus 1 times p into 1 minus delta. But what is each di equal to? So if I take, let's say, d1, This is summation j equal to 2 to n of indicator random variables. Right? So it's basically a sum of Bernoulli random variables. Correct? And we already have a tail bound for Bernoulli, for sums of Bernoulli random variables. So what can I say about this? So I know that the probability that the sum of Bernoulli random variables being greater than or equal to their expectation times delta, right, is less than or equal to 2 times e to the minus n delta square p by 4. So I can just plug this in. So this is n times 2 e to the minus n delta square by 4. So there's a p delta square p by 4. Now if p is much larger than, let's say, 1 over n, right, what happens to this particular quantity as n tends to infinity? It tends to 0, correct? So in fact, with very high probability, no matter how small, as long as delta square p is greater than 1 over n, this quantity tends to 0 as n tends to infinity. In fact, delta square p should be larger than log n over n, right? So if that happens, then this quantity tends to 0 as n tends to infinity. And I could say this just because I had this kind of an exponential tail bound. So remember delta, so suppose I take p to be a constant independent of n, then delta square can be like very, very small, right? So it means that actually the number, the degree of each vertices is very, very tightly concentrated around its mean, right? The deviation from n minus 1 times p is very, very small, correct? And I could do all of this because I had this exponential tail bound. If I use something like Chebyshev inequality, I would get probability of E1 to be something like some constant divided by n, right? So as n tends to infinity, I would not be able to make this right hand side tend to 0. But in this case, I can. Right? So let's stop here. We're out of time, but we can continue later.